Okay, good morning. I hope everyone had a good weekend. So let's go ahead and get started. So today we're going to do another couple examples in chapter 5 in your textbook. Okay, so we'll do example 5.5 and example 5.6. So we're doing two today, but they're both pretty short. And then those will be due same time as always next Tuesday. So let's go to the Blackboard page. All right, so you can open up the Word document, which is the example 5.5 and 5.6 items. All right, and the first Excel file will be the shortest path one, so you can open up that one first. Okay, so we're going to do today a couple shortest path models, and the concept is very literal. At first, you're just trying to kind of minimize the distance between one point and another, and so you're trying to literally find the shortest path or the shortest distance. But we'll see if we can apply this concept to things that aren't just physical distance. You can find it for like replacement items and the number the length of time you need to keep a machine or a computer or something like that. And so we'll first learn about shortest path just by looking at a literal shortest path problem, and then we'll see how we can apply it to some other business solving models. All right, so let me first start. So there's an optional video you can watch on shortest path. So take a look at that. It's maybe 5 or 10 minutes. Okay, and let me introduce read the description for the shortest walk across the state, which is example 5.5 in your textbook. All right, so Maud Jenkins, who's a 90-year-old woman, is planning to walk across the state, west to east, to gain support for a political cause she favors. She wants to travel the shortest distance to get from city to city. To go from city 1 to city 10, that's the goal. Using the arcs, or the roads that are allowed here. And so the number of arcs, numbers on the arcs are miles. That's how many miles it takes to get from that city to the next. And it shows some of the arcs have double-headed arrows or double-sided. So those ones you can go either direction, and the ones that are only single-sided, obviously you can only go that direction the arrow is pointing. Okay, so what route should Maud take to minimize the distance? She's 90 years old, so she doesn't want to walk as much as she wants to walk as little as she can. And so the goal here is to get from city 1 Alright, so the goal is to get from city 1 to city 10, as you can see here on the network diagram. And so there's all these other in-between cities, and so the distance between each point is those miles. So like going from city 1 to city 2 would be 70 miles. Going from city 2 to city 7 would be 79 miles. And so we're going to do a simple model where she can walk the minimum distance possible, but she's got to go along for the route. So what is the shortest path? You could probably figure this out if you did, a bunch of different trial and errors, but it's probably easier if we use Excel Solver to figure it out. So let's minimize the walking distance from city 1 to city 10 for Maud Jenkins. Okay, so let's go to the spreadsheet. Okay, so it's a very simple model, but it explains the concept of shortest distance in the literal context, which is walking the shortest distance. So you'll see here that we have the network structure. So these are all the options she can walk from. So city 1 to city 2, 70 miles. City 3 to city 5, that would be 69 miles. And so all the options are here. And so there's only one person going along the route. So the flow that we're going to choose are either going to be 1, she chooses it, or 0, she doesn't. So a very simple model, but it explains the concept of shortest distance, and obviously the objective is going to be to minimize total distance by choosing the number of flows here to get from city 1 to city 10, and we have the slope constraint like we've had on some of the network models, which means that it's a zero-sum game, so we have to count for the one person for the whole network. So let's start doing this one. Let's go to the word. All right, so first thing we'll do is set up the model with the highlighting and then make some range names. So there's not much going on here, but we've got to set it up. So let's go back to the spreadsheet. Okay, so the distances, those are inputs. Those are set by how the physical distance from one city to the next. So you can highlight the distance column, light blue for inputs. Okay, so C5 to C39, that's light blue. We're going to choose the flow or not, but the decision variable range for most of these network diagrams is the flow. So this whole area is our decision variable range. So you can highlight the D column next to the distance column. You can highlight that light red for decision variables. So D5 to D39 is light red for decision variable. And the other thing we got to show here is, the objective is total distance. So let's highlight B42, the highlight yellow color. That's our objective. Okay, and our only constraint is that our net outflow has to equal the required net outflow. So when we specify this in Solver, we're just going to say that this net outflow is equal to the required net outflow. So just show that there's no inequality, there's just an equal sign. So all the nodes, the required net outflow has to equal the net outflow, so just put an equal sign here in H5. And that's got to be true for all of them. So just put an equal sign to show the constraint in H5 to H14. Alright, so that's our constraint right here, that all the net outflows at each node have to equal the required net outflows. Okay, so we're going to make range names for pretty much everything, but there's not very much to make range names for. So you can make a range name for origin, destination, distance, and flow all at the same time by selecting them all. So if you select A4 to D39, and we can make 4 range names together like that. Alright, so 4 nodes, and then create from selection. And if you want to choose top row to give it the 4 range names. Alright, you can also select A42 to B42 and make a range name for that. Okay, and then we also want a range name for both sides of the constraint, so you can select G4 to G14 and make a range name for that. And then you can also select I4 to I14 and make a range name for that. Okay, so let me pull up the name manager and let's see if we all have the appropriate range names in. Yeah. Okay, so you should have a range name for destination, distance, flow, net outflow, origin, required net outflow, and total distance. Alright, so double check those. Everyone got the range names and everything so far? Okay, so great. Let's go on to the next step. Back to the Word document. Okay, so this step is already done, the arc list. So if you were starting a network flow diagram with shortest distance, you would first have to list, in a row all the possible arcs. So that's done here in columns A and B. Okay, so all the possible flows are listed here from origin to destination. So that's done, but that's the first step. If you were starting this model from scratch or any network model. Okay, so let's calculate the net outflows in the constraint area. So let's put in the SUMIF function in G5. All right, so in G5, put in the formula you see in step 2. Okay, so here's your formula. It's equals SUMIF, origin F5 flow minus SUMIF, destination F5 flow. So this should be the same concept we did from the previous network model. Remember the tomato product one, where we're specifying what goes out of the origin minus what goes into the destination. And you can see that it coincides with node 1. See the F5 is the indicator for node 1. And we're going to do the same for all of the other nodes, but it's got what goes out of the origin minus what goes into the destination is going to be equal our required net outflow that we're going to have to account for mod Jenkins. So that's your first formula. So make sure you got it because we're going to copy it down the column here. So again, minus or equals SUMIF origin F5 flow minus SUMIF destination F5 flow. And let's hit enter. And let's apply that formula to the rest of the nodes. So if you got the formula in G5, just grab the bottom right corner and drag it down the G column like this. Okay, so if you tab down, you should see it's the same exact formula. The only difference is it changes the indicator for the node. So it should go all the way from node 1 to F14, which you can see here is node 10. Okay, and then we need to specify the constraint to account for the one person in this model. So to do that, like I said in step 2, put a 1 in I5. Oh yeah, sorry. Let's. Okay, so here's the equation that we put in G5. So it's equals SUMIF origin F5 flow minus SUMIF destination F5 flow. Okay, and then once you type that into G5, just apply the same formula down. So grab the bottom right corner. Okay, so once you have this formula, just drag it down like this. Okay. Taylor, did you get that formula there? Okay, you're welcome. So we got that step, and then we need to set up the required net outflow to just account for the one person that's going from point A to point B. So just put a 1, again, in I5. Then put zeros in the middle portion, so put a 0 here. And then you want a 0 from nodes 2 to 9, just like this. And with node 10, put a -1, and so this will make sure that it's a zero-sum game, so there's no more people or items in the nodes after the model is solved. So there's a -1 here. So this part, just type it in. Just type in a 1 here. Type in zeros in the middle. And then the last one for node 10, -1. So just make sure that your required net outflow looks like this, because that way it'll solve the constraint for a zero-sum game. Okay, then the next step is just to calculate the total distance, which is the objective. Okay, so you can just put in the sum product formula in cell B42 for the objective. Oh. Before we do that, let's put values in our flow column that we haven't done. So let's just put zeros in here for now. So starting in D5, put a 0 in there. And you can apply the 0 in the whole flow column. So we need values in there for solver to change. Okay, so D5 to D5 to D39, just put zeros in there, and then solver will find the appropriate flow if necessary. So put zeros in there. Then back to step 3, the total distance. So in the objective formula, in cell B42, type in this formula, and that you see in your step 3 equals. Alright, so it just equals sum product, distance, comma flow. And so this is obviously literal. Alright, so the total distance, if she chooses to go along that route, then there's a 1 in here, so you add the distance. If she doesn't, then you don't. So just the sum of all the routes she chooses is our total distance. Right? So all the ones we choose will be added the distance, and all the ones we don't, we won't add the distance. Okay, so equals sum product distance comma flow. Okay, so the next thing we're going to do is just solve the model. So we're gonna minimize total distance using the solver. And so let's solve the model and see what routes that will give us the shortest distance from city 1 to city 10. So back to the spreadsheet. Okay, so let's run the solver. Data. Okay, so data tab and then solver. Okay, so the objective is the total distance cell, so choose this and select B42 for the objective. Okay, and we're going to minimize that, so make sure you change this to minimize, to min, so shortest distance. Okay, we're going to change the whole red column, which is, we made a range name for it called flow. So you can just type that in because it'll recognize the range name. So by changing variable cells, just type in the range name of flow. Right, so that should give us the appropriate range name that we defined, hopefully. And we have one constraint. Let's specify that. So subject to the constraints, click on the Add button. And we need to specify that net outflow equals required net outflow. So go ahead and, for cell reference, click on the button and choose G5 to G14. And the middle sign should be equals to, so change it to equals, right? And the constraint, click on the button and choose I5 to I14. So this one, the constraint is G5 to G14 equals I5 to I14. And hit the OK button. Okay, and make sure down here where it says the solving method, switch that to simplex LP. And so let me run through the options, and then if we need to get any steps again, I can do that. So the objective is total distance. Make sure we're minimizing that. We're changing the flow column, so all of the red cells. The only constraint is net outflow equals required net outflow. Make sure that box is checked, and the solving method is simplex LP. Okay, so anyone needs steps repeated for the solver before we solve it here? Everyone's solver parameters look like this. All right. Well, let's hit solve and see what happens. All right, and hit solve, and then if you get a solution, hit the OK button. And this is what I think we should have gotten: a total distance of 198 miles. And so that is the shortest you can do. So you can see that she chose to walk from City 1 to City 4, 56 miles. Then from City 4 to City 6 for another 45 miles. And then finally, from City 6 to City 10, that was 97 miles. If you add all those together, that's the total distance, which we got, which is 198. Okay. Did we get that same solution? Did we get 198 for the distance? Yeah. Let me pull up the solver again. Alright, so there's your solver parameters. So look over that and see if you needed to redo any steps. A total distance of 1. Okay, so something's wrong probably with the actually, okay, just alright, so okay. Do you wanna, if you post your Excel file to the discussion forum, I can look at it real quick? Alright, so just post your file to the discussion forum, and I'll look at it when you post it and see what I can figure out. Oh, okay. So your objective function is not right. So this should be the sum part. So in B42, this should be the formula, not the one you have. So try putting that formula in B42. All right. Erase the other one and put equals sum product distance flow, and then try running the solver again, and hopefully that works. Okay. You're welcome. Okay. So everyone else got the 198 for this one? Okay, so that's we have another exercise to do, but we're pretty much done with the example 5.5. So that one you can save. And the last part was the network diagram. So we don't have to do this part because I can't really draw, but I mean I can draw, but not on the computer. So what this part meant is if you wanted to show like a flow chart of the solution, you could draw like the network model and list the flows like this. Alright, so what the diagram solution looks like is just, you would show the options that we chose. So if you chose to go from 1 to 4, so you can show that right there. And with the 56 miles, then she chose to go from 4 to 6, so you can show that from there to there. With the 45 miles, then she chose to go from 6 to 10 with the 97 miles. So the network flowchart solution will just be showing this to this, this to this, and that to that. And you don't have to do that, but I'm just saying how you can show this as a flowchart. Alright, so we're done with this one. So you got the 198 with the options, so you can save this. Okay, so that goes in here for example 5556. So we still have to do example 5.6. So you can either post two separate posts, or you can post them together, whatever you want to do. So let's do example 5.6. All right, so let's open up the Excel file under example 5556. On Blackboard, this says machine replacement. All right, so this one we're going to use the shortest path technique to apply it to another business model. So this one we're using shortest path, but it's not actually a distance. It's just the shortest time. It's the same concept applied to a business model. So let me see if I can find the description for example 5.6. All right. Quite a long description, but all right. So this is equipment replacement at Van Buren Metals. So Van Buren Metals is a manufacturing company that uses many large machines to work on metals. These machines require frequent maintenance because of wear and tear. And Van Buren finds that it's sometimes advantageous from a cost standpoint to replace the machines rather than to continue to maintain them. So this is just like, at some point when you have an old car, and if you go to get repairs and the repair cost is more than it would cost, to sell the car, then it's probably time to get a new car. So the same concept here. When it becomes too costly to maintain due to maintenance, then from a cost standpoint, it's best to replace it and not keep throwing money away for maintenance. Okay, so for one particular machine, the company decided the quarterly cost of maintenance, the salvage values, from reselling the old machine and the cost to purchase a new machine. So we assume the maintenance cost and the salvage value depend on the age of the machine. So the longer you go on, the more expensive the maintenance is. Okay, but we're not assuming inflation, so this is a simplified model. And if we were doing a real model, we'd probably have to incorporate inflation, or convert the cost to a specific basket. But for now, let's assume that there's no inflation to simplify the model. Okay, so it costs $3,530 to buy a machine. The maintenance cost of the machine in the first quarter was $100. And for each succeeding quarter, the maintenance cost increases by 65. Right, and so this is because the longer the machine, the more wear and tear, right, the more maintenance is required because more stuff can go wrong the longer you wait and the longer you use the machine. Okay, the salvage value of a machine is $1,530 after one quarter, and then each additional quarter, the salvage value decreases because it's worth less over time, so it decreases by $110 each additional quarter. Okay, so what we're going to do is use the shortest path technique to devise a strategy for purchasing machines over the next 5 years. And the company policy is it never sells a machine that's less than a year old, and it never keeps a machine more than 3 years. So we have the constraints there, and also the machine in use at the beginning of the current quarter is brand new. So there's a lot of information there, but basically what we're going to do is we're going to develop a minimum cost strategy using the shortest path model, and find the best strategy to replace these machines. So what's the point at which it becomes too costly to keep maintaining a machine, and you got to replace it. All right, so let's go to the model. All right, so step one is to set up the model and then create the range names. So I guess this part. So first, let's go to the spreadsheet and let's highlight our inputs and objective and decision variables, and then we'll do the range names. So go to the machine replacement spreadsheet. Okay, so all the inputs are right up here. So the purchase cost, the maintenance cost, and the salvage values that we just talked about. Highlight all those values. Light blue for inputs. Alright, so all those inputs under the input header are inputs. So those are light blue. Okay, so we are going to decide the flow of the optimal solution. So this is going to be the decision variable range. So this whole area is going to be light red. Okay, but it's all the way to 130. So let's see. Okay, so select S14 to S130 and just color that light red for the decision variable range. All right, so S14 to S130. Okay, and let's put values in there for now since we're here. So you can just put a 1 in the flow column for all the options, and then solver's going to figure it out later. So for now, just put I'll put a 1 in S14, and then I'm just going to grab the bottom right corner and apply it down for all the light red cells like this. Okay, so all we've done here is in S14 to S130, highlight a light red for decision variables and put 1s in there for now, and then solve is going to figure out if we choose it later. So it's a big range, but those are all the possible decisions that we can choose when the solvers run. So again, S14 to S130. Okay, we have one constraint, the flow bound constraint over here. So this concept is the exact same as we did with the shortest distance walk. So the net outflow has to equal the required net outflow. So to show the inequality or the constraint, just put an equal sign in W14 and apply it down for all the other nodes. Right. So in W14 to W34, just put an equal sign to show where we're going to make the constraint. Okay, net outflow equals required. And then if you go over here, you should see the objective, which is total cost. So this V36, highlight that, the highlight yellow color for the objective. Okay, so let's see. We're gonna make the range names next, but these are the inputs. We're choosing all the flows in the S column. This is our one constraint over here, the flow bound constraint. And the objective is to minimize total cost. Okay, so I think I put the range names that we need to make. So the range names we need destination, flow, net outflow, origin required, and total cost. So let's make those range names, and then we'll start calculating the model. Okay, so we need a range name for origin and destination, so you can select both of these, or this whole block together. So it's a big range, so select A13 to B130. . 130. And then with all that selected, the same step, formulas create some selection. And it should choose top row, hit OK. So we'll have a range name for origin, and then a second range name for destination. So top row, OK. We need a range name for flow. So you guys set this up, but select F13 to S130. So select all that and make a range name for the flow area. And F13 to S130. Okay, then formulas, create some selection, top row, okay, and that'll make a range name for the flow. Okay, so now we need a range name for both sides of the constraint and then the objective. So net outflow. Select V13 to V34. V13 to V34 and make a range name for that. And then for required, so X13 to X34. Okay, then make a range name for that. And then last, I think, is total cost. So if you just choose U36 and V36 and make a range name for that, that's the last one. All right, so let me get the name in here. Let's make sure we got. I think there's only 6. All right, so you should have a range name for destination, flow, net outflow, origin, required, and total cost. So those are the 6 that we just defined. And so everyone got those range names? Everyone get so far? All right. So let's move on to the next step. Okay, so the input's already done in column D. So we've already done that part. The arcs are already listed in column A and B, so we've already done step 2. All right, so all the origins and destinations are listed. All right, so for example, we start with the machine in quarter 1 and we keep it until quarter 5. That's an option. Or there's a whole bunch of options, but this is what these mean. So you get a machine in the first quarter and you keep it until quarter 6. And so you kept it for 5 quarters. So all the options are listed for how long we can keep the machine if we want to. All right, and then step 3, quarters to keep. So this, I believe, is already done too. So this is just specified the difference between the start quarter and the end quarter, and that's how long you kept the machine. Yeah, so that's already done. So, for example, if we start in quarter 1 and we keep it to quarter 5, we kept it for 4 quarters. If we start in quarter 2 and we keep it to quarter 6, we kept it for 4 quarters. So this will determine the cost, exactly how long we kept the machine. Okay? So it doesn't matter when we start and when we end. What matters is how long we keep the machine. Okay, so now we have to start putting in these formulas. So step 4, we have to do this. We're going to put this big formula in D14, and we're going to copy it to a big range. So let's go back to the spreadsheet, and in D14, type in this formula. All right, let me run through this one, see if we got it. All right, so in D14, the formula is equals if $13 is bigger than $C14, comma 0, comma $B, $6, plus $B, $7 times, in the parentheses, $13 minus 1, and then double parentheses. Okay, so make sure you got this formula, then I'll explain what it is. But there's the formula. And so again, make sure the dollar signs are in the right spot, because we're going to apply it to all the other quarters. All right, so let me hit enter, and then let me explain what the formula implies. Okay, so you should get 100 for now. So this says if the current quarter, right, so it's quarter 1, is bigger than okay. So if the current quarter is bigger than how long we kept it, all right, then put a 0 there. And otherwise, okay, so this is specifying the appropriate maintenance cost. Okay, so just look at it literally here for now. So if D13 is bigger than C14, 0. Okay, if not, this is bigger than this. So instead, it's going to be $100 in the first quarter plus an additional $65 each additional quarter, which is this quarter minus 1. Okay, so what this is saying is that it's just specifying the maintenance cost. It's saying that if we kept it for a quarter, the maintenance cost is 100, and each additional quarter, it's another $65. So this is only the cost part, all right? So this is saying if we're in quarter 1, the maintenance cost is $100, right? So the first quarter, it's $100. if you buy the machine, it's $100 per quarter, or in the first quarter. So in the first quarter, it's $100. All right. So hopefully this will make sense when we apply it to the other quarters. But if you have this formula correct in D14, you can grab the bottom right corner and drag it across all the way like this. Okay, and the way the formula is set up, it's if you the maintenance cost is $100 the first quarter, plus another 65, plus another 65, plus another 65. We don't keep it. We only keep it to quarter 4, so we don't have it for these other quarters, and therefore the maintenance cost only is 0. You see how we did that? You keep this machine from 1 quarter to quarter 5. So maintenance cost is 100 in the first quarter, plus another 65, plus another 65, plus another 65. Then you get rid of it, right? So there's no more maintenance cost. Okay. Now, if you got this part set up, we're going to apply it down the entire, area. So select D14 to O14 and grab the bottom right corner and drag it all the way down like this. Okay, so what we're doing is we're applying that same exact formula to calculate the appropriate maintenance cost for all of the options. Okay, so hopefully we got the appropriate maintenance cost for all the network arcs. And did everyone, did we get that step?
Yes.
All right. Okay. So if we got that, that's the biggest step is to get the right maintenance cost, because you can see that the formula is slightly complicated, but it should make total sense when you see the numbers, where it's $100 to maintain it, and then each additional quarter is 65. And then once you get rid of it, there's no more maintenance costs because there's no more machine. Okay. The next step is to calculate the salvage value. Okay, so let's put that formula in P14 and then copy it down that column. Okay, in P14, put in the formula you see for step 5. Alright, so in P14 equals $B, $9 minus $B, $10 times, parentheses, C14 minus 1, and then close the parentheses. So there's the formula. And we should get 1200 for now. And what this does is it's the salvage value based on how many quarters we keep it. So you can see that it's the salvage value is 1,530 after 1 quarter, and then each additional quarter, the value decreases by 110, and so you multiply the 110 times the quarters you kept it minus 1. So basically, this is saying the salvage value is, if you kept it for 4 quarters, the salvage value is 1530 minus 3 times 110, right? So that's exactly what it should be, is because for the first quarter it's 1530, and then minus 110, minus 110, minus 110, and that's the depreciated value given the fact that you kept it for 4 quarters. Okay, and if you got that formula there, in P14, just grab the bottom right corner and apply it down, like this. Okay, and you should get all the salvage values there, and you can see that the longer we keep the machine, the less we get for it, right, because it depreciates. Alright, step 6 is to calculate the purchase cost. This is easy, just put the $B, $4 in Q14. Okay, step 6 in Q14 equals $B, $4. Okay, so the purchase cost is always the same, which is indicated in the input. Okay, so the purchase cost is always $3,530 if we buy it in that quarter. So you can see that's what's going on here. Okay, so then just take the formula in Q14 and drag it down for all the purchase costs like this. So in all the purchase costs, you should just have $3,530. Right? Next step is to put in this formula to calculate the total ARC cost in cell R14, and then we'll apply it down the R column. Alright, so step 7 in R14, put in this formula. Alright, equals sum G14 to L14, and then minus P14 plus Q14. Alright, equals sum D14 to O14 minus P14 plus Q14. So what this is the total cost based on the maintenance cost, the salvage value, and the purchase cost. Okay, so the total cost is the sum of all the maintenance is required. Alright, so that's the maintenance cost. And then if we sell it, we get a refund basically of $1,200. Alright, and then the purchase cost was $35.30. So the total cost is the purchase cost minus the maintenance cost plus the salvage value, if any. Okay? So that's it there. And the total cost for this option should be $3,120. And let's apply the formula down the total cost column. So just grab the bottom right corner of R14 and drag it down like this. Okay, so you got that total cost formula in all the options. Alright, so step 8, I think we've already done this, is put any flow values in column F, and solver's going to find the optimal flow, so we did that already, right? Yeah, so make sure you got, we've already done this, so you have 1s in the flow column too. Alright, so S14 to S130, we got 1s. Alright, and then we just need to specify the flow balance constraint, then the total cost, and then run the solver. Okay, so let's go back to the spreadsheet. Okay, so for net outflow in D14, alright, put in this formula. Alright, so the same exact concept from the previous shortest path model. So we're calculating the net outflow, which is what goes from the origin minus what goes into the destination from each node option. So see how the U14 is for node 1, and so the formula for this one should say equals sum if origin U14 flow minus sum if destination U14 flow. Okay, so for node 1 only, what comes out of node 1 minus what goes into node 1 is the net outflow. Okay, and you should get a 9 there for now. Then, if you got that formula in V14, just grab the bottom right corner of V14 and drag it down to get the other nodes. Okay, so if you did it correctly, you can see that the same formula applies now to node 21 right here. See how the U34 is indicating the node 21? Okay, and we have to specify the same logic that we did like with the shortest path model. So in x14, put a 1. In x15, put a 0. Alright, and we need a 0 in all the middle nodes like this. And then we need a -1 in x34. Okay, so for the required constraint, you're just typing this in. So right here, 1, then a bunch of zeros, and then the last one is going to be -1, so it all sums to 0. Alright, and then the final step before we do the solver is just to calculate the objective, the total cost. So in V36, this is equal to, alright, in V36 is equal to the sum product. Why is, oh, okay, so the total cost has already been used, so we need to, or we didn't make a regime for the other total cost, so let's do this. Okay, so in V36, here's the formula, because we don't have a range name for that column, is sum product R14 to R130, comma flow. Okay, so there's the formula right there. Okay, so if we choose that option, then we just add the total cost. If we don't, then we don't add the total cost. So the sum of all the options is going to be the total cost with this strategy. And so it's going to be 1 times the total cost, otherwise it's just 0. So see how it's all the total cost options times the flow. Okay, so if we choose it, we add the cost. If we don't add the cost. Alright, so again, that formula is equal to sum product R14 to R30, comma flow. And that's what we got for now. We're going to get a different solution when we run the solver, but at this point, I think you should have 614, 130.
Sorry, Professor, I got value.
Got value? That probably means that it didn't, like, so in the sum product, do you see that this is highlighted? Like the same number of, like, is the same column here, the same column here?
Yeah, I do.
Okay, and alright, so let me, okay, do you want to post yours? I'll look at yours.
Thank you.
And Trevor, I can look at yours too if you want. Okay, and then everyone else okay so far? Yours is just to see how the flow column is just one, like it's, so some products doesn't work if it's not the same number of cells. So see how there's an extra one? So just do this. Alright, so change it to equals sum product R14 to R30, comma S14 to S130, and then that should work.
Thank you a lot.
Okay, did that work? Yeah?
I got it. Thank you.
Okay, you're welcome. Alright, so this one. Okay, and then I think you sent me just a blank file, Trevor. Alright, well, let me just start setting up the solver, and then I'll look at yours in a minute. So, if you got everything for the model, the only thing you have to do last, we're pretty much done, is run the solver. So, go back to the last step is just minimize total cost. So, when you got the spreadsheet open, just click on data. Alright, so data solver, and let's just set up the solver and then solve it. Alright, so let me look at this one, and then we'll come back to the solver. Yeah, I think you sent me the same one again. All right, so let me do the solver, then I'll come back to you. All right, so yeah, we can. So okay, data solver. Okay, so our objective is total cost. So the objective is V36. Okay, make sure you flip that to minimize. So we're minimizing that. The nice thing here is we know the decision variable. That range is called flow. So just type it in. Let me select it because I know that some students didn't have the range name right. So by changing variable cells, hit the button and choose S14 to S130. Okay, so by changing variable cells, S14 to S130, and then we have one constraint. Click on the Add button. The constraint is that net outflow has to equal required. Okay, so cell reference, click the button, choose V14 to V130, sorry, V14 to V34. This is equals, and the constraint is required. So hit this button and choose X14 to X34, and hit OK. So here's the constraint V14 to V34 equals X14 to X34. Hit the OK button. Change the solving method to simplex if it's not. And these are what your parameters should look like. So look over this before we solve it. Objective is total cost. You're minimizing that. You're changing the flow. Your only constraint is net outflow equals required. This is checked, and this is simplex LP. Alright, and if this doesn't say flow, just make sure you selected the right range, because if you didn't have the range name specified in the right range, it doesn't matter as long as you selected the range I showed you. So look over the parameters and let me know if we need something repeated here. Alright, let's should we solve this? Let's hit solve. Hopefully we get a solution and hit OK. And the solution we should get is 13,575, and you can see that it shows. So this is the strategy we chose. We chose to buy a machine in quarter one, keep it for 7 quarters, or we keep it for quarter 7, so 6 quarters, see? And then we kept it for another 7 quarters, so we salvage it in quarter 7, get a new machine, keep that one for 7 quarters. That was the minimum cost, and then I think we keep it for another 7 quarters. Yeah. So the best option for 21 quarter period is we decided the minimum cost solution is to keep it for 7 quarters, replace it, and then do the same every 7 quarters. So that's what we chose to do, and hopefully the minimum cost we got, or some of us got, is a minimum cost of $13,575. Okay, did we get that solution there?
Yep.
Yeah? Okay. Yeah. All right, so that concludes this one. All right, so this is for example 5.6. So the ones we just did, so the shortest path file and the machine replacement file both go in here. All right, those are the exercises we did for example 5.5 and 5.6. So make sure you post those by next Tuesday. We're just about done for today. All right, so those two are done for today. Those are due next Tuesday. We'll do example 5.7 on Thursday. Yeah, and then Trevor, I can look at yours, but everyone else, if you're done with the exercise, that's it. And have a good rest of your week, and I'll see you on Thursday morning.
Professor, I had a question about the assignment due today for Monday's class.
Okay.
Because I did it and then I waited and I tried to redo it again, thinking maybe it was just like my computer. But then when I rewatched the video a few times, a lot of other people had problems with the solver also. So I submitted it with the solver and a screenshot of my solver with all the stuff on it, and it says it's the exact as it. I just don't know why it wouldn't solve.
Okay. Well, if you hold on a second, let me look at Trevor's for this one, and then I'll look at yours for that one.
Okay. Yeah.
All right, here we go. So let's see. So Trevor, it looks like you skipped or didn't put the formulas in quarters 11 and 12. So I think that's it. Let's see. Yeah, that was it. So just see what I did with yours. So apply those formulas in the quarters 11 and 12, and then rerun the solver. And then I did that and it worked, so try that. Okay, and then let me look at, so what was the example from last week that you were talking about?
Oh, it was 4.8. And I thought it was my solver, but then when I was in class on Thursday, my solver worked fine, and then today it worked fine, so I don't know what the heck's going on. Yeah, 4.8.
Okay, this is Jessica?
Yes.
Okay, so this is the one here? Yeah.
Yes. Because I think it got to a point where the solver, and then we had like multiple other little exercises, but it was relying on the solver. So I was like, if my solver's all messed up, there's nothing really I can do.
Okay, let's see.
And then I remember like other students had this problem, at least in the video, so that and when you ran it on yours, it worked. But when we opened it on ours on the MacBooks again, it went back to 0.
Yeah, see, I think I just worked again.
Yeah. I don't know. And then I tried doing it on, you know how you can do Excel through Laverne on the website, like online. They don't have Solver, or at least mine doesn't have Solver on that Excel on the one that Laverne gives you, so I couldn't even run it there. So.
Oh yeah, the online version you can't use Solver. You gotta use the full version. So I don't know. Yeah, I just ran it again and it worked. So let me try it for the other one.
What? Every time I changed it 1, 2, 3, 4, it just gave me 0.
So the only thing is, like, these might be my solver. Like, it might have defaulted to my solver. So I know your model's 100% correct. It doesn't mean that the solver is exactly what mine says, because, like, whatever your solver did last, it goes back to that.
Okay.
So I would say, on your computer, if you can pull up your solver and look at that, make sure it's exactly like this. If it is, then I don't know what the problem is, because the model's fine, but it doesn't mean that my solver is exactly what your solver says. Cause
Okay. Mine. Okay, mine says that.
and well, I guess that works for Trevor if you like.
Now mine, like, weirdly, when I opened it, oh, actually, hold on, it's because in the model you created another sheet.
Okay, so can
Yeah,
you...
it says $B, $22, then maximum, and then $B, $10, colon, $C, $10, comma, $F, $10, colon, $H, $10, constraints, $B, $14, colon, $B, $16, greater than, equal to, $B, $14, colon, $B, $16, yep, and then $B, $19 equals $B, $19. So click the make unconstrained variables and then simple LT.
Yeah, and your solver doesn't work?
It just says 0.
I don't know. There must be something with this.
I thought it was my solver at first because like, I have a MacBook, but then when I did our exercise on Thursday and then our exercise today, it worked perfectly fine. So I don't know what to do.
And this is the only one that it did.
Yeah, this is the only one that it's missing the solver at least.
Okay. Well, I don't know. Don't worry about it. It must be just some, discrepancy between the Mac solver and this one, but.
Okay. I noted it in the discussion that if you saw that my professor my solver wasn't working. So is that fine for right now?
Yeah, it's 100% correct because some other students have the same problem. So yeah, you're good on this one. Don't worry about it. And you'll still get full credit.
Thank you. I appreciate it.
Okay, you're welcome.
Have a good one, Professor.
You too.